Hi everyone, good morning. Thank you so much for joining us today. Uh, I know this is the first talk of the day and I'm really excited to present something, one of the research that we had recently done. So I'll quickly give an introduction about who am I. So my name is Nikhil Prabhakar, as she mentioned. Uh, are you guys hearing an echo by any chance? No, right? Okay, I'm hearing an echo, so that's why I asked. All right, so I've been in the security industry for almost 10 years now, and I started off as a pen tester and eventually moved my way up to looking at DevSecOps and the defensive side of security. Now, in terms of my contributions, I've been an active member of the Null community and I've been leading the chapter, the Bangalore chapter for Null. And it's been coming out really well. And I've been an old school bug bounty hunter listed in the Hall of Fames of Microsoft, Apple, Adobe, and a bunch of others. Currently, I'm leading the security engineering at this wealth management company called Deserve. And yeah, that's pretty much about me. I'll quickly give you guys the agenda, what exactly we are trying to look at in today's session. So fundamentally, we are trying to understand if we can do a malware analysis using machine learning algorithms. Of course, you would have seen quite a lot of people doing it already using neural networks and a bunch of other things. I have taken a particular algorithm and this experiment is all about that. What was the false positives that we got, what were the true positives, true negatives, etc. All right, so I'll quickly give an introduction about this. So we call this as Flame framework. It's a project that we had built using the open source Python libraries. And the whole idea here was to first extract the label call graphs for Android applications. First we would basically reverse engineer the applications into the DEX formats and then eventually look at these functional call graphs. And post that we would map these call graphs and then devise as to how we'll be able to extract if a particular application is a malicious or not. Okay, so that's the fundamental idea here. So why did we even come up with this project? So some of the very obvious reasons have been that Android being like the largely used mobile application, mobile operating system overall, and I think more than 1 billion devices are currently running Android. The third being extreme digitization. Currently, you see most of our tasks that we do are all using our phones, right? Finally, the fact being that there are quite a lot of third-party app stores that are coming up right now. I think there's one that's quite recently launched by one of the payment providers in India as well, if you see, right? So there were a bunch of reasons that we decided to go with running this project. Okay, so the fundamental objectives and the goals for this experimentation that we had was check if machine learning algorithms could be used to differentiate between a malicious and a non-malicious Android application, right? And this we decided to go with functional call graphs. I'll tell you the reason why we even decided to go with this method. We did look at a bunch of other mechanisms as well, but then we finally decided to go with this. And we would eventually be computing the similarities based on the structural objects. So I know sometimes a couple of words that I'm going to be using might be very specific to machine learning world, but I'll try to sort of simplify it as much as possible. All right, so the formal problem that we see was, can the machine learning be used as a way to perform Android malware analysis? And this we try to find using different hypotheses and quadratic equations if we could make these graphs and then gain the insight out of it. Okay, so yeah, so there were already available bunch of models that were available, such as unsupervised k-means clustering algorithm. One thing that we really found out here was we ended up with large amount of false positives there. And I think there are a bunch of people who have already worked on supervised mechanisms using random forests and bunch of others. Of course, the people who have used even neural networks, I think a couple of new models have also come out, right? Our focus was very specific to this algorithm called SVM, support vector machines. I'm sure most of you would have already heard of it, worked on it, yeah, or probably would be exploring it as well. Okay, so I'll give you the model in a nutshell. So the core idea here was that we start with the collection of samples. When I say collection of samples, these were malware samples as well as non-malware samples, benign samples, right? And to eventually also go ahead and perform the static analysis to extract the call graphs. Now this, of course, we used a tool called JADX, and we were able to then decompile the APK files and then look into the format and then generate a functional call graphs. So I'll talk about what exactly is a functional call graph and all of those aspects. And then we would extract the features, based on these functional call graphs that we get created. There would be features, particular to those applications that would get extracted, and then the analysis would happen based on the SVM algorithms, right? So that is pretty much the mechanism that we had taken here. So when I say data sets, again, so we took around, sorry, there is a bit lag with this screen and this screen here, so sorry about that. Okay, so we took around 900 malicious samples and 900 non-malicious samples. Of course, the next question would be, where did you even get malicious samples? Of course, people who are in the security industry, they know where to get it. There were a bunch of online forums. I don't know if you have heard, there was this blog spot called Contagio Dumps. Long back, quite a lot of people used to get malware samples out of it. Of course, there are a bunch of other places also where you can get them online. So we were able to create the data sets based on these two varied samples, malicious as well as non-malicious. The reason that we took 900 specifically for both is to have an equal amount for both malicious samples as well as non-malicious, just to ensure that it's not like weighed in too much on the malicious side and so that it would impact the final outcomes of it. All right, so what are the initial set of parameters that we ended up collecting? The initial set of parameters was for us to basically map with respect to those application and their respective features. So we decided to collect things like app name, application size, calculated SHA-256 hash value, what is the app type, what are the permissions that are given, etc. All of those aspects, right? Again, these would actually weigh in like at a very minimal quantity in terms of the entire analysis that was done, okay? But these were like the initial parameters that we collected. Okay, so I'll talk about something called as feature space, right? In SVM, so if you take up a support vector machine, the entire space is considered as a feature space. Now, what are the aspects that were taken in for the feature space, where the functions of these of these applications and their API names and the API calls that they ended up making, right? So I know quite for the larger audience, it might be a little confusing as to understand what exactly is a feature space and all that. When we get into the SVM part of it, you will really understand what exactly I'm trying to tell here. Okay, so let's look at the functional call graph, right? So let's consider this. So in any language, if you take, so there is, let's say if you take even C language, right? So you would first have your main function. So whenever you run an application, the first function that gets called is your main function. And only post that, it goes into the different set of functions, right? So the functional call graphs initially were generated using this mechanism where we started off with a particular function and then it eventually goes into looking at creating other functions, right? Call graphs based on these functions. So that's how we are able to sort of create a structured graph out of it. And post that, I think, yeah, I'll start. So the way we were able to sort of look at it is like, for example, if you consider these two examples here. So these are different set of graphs, but the kind of nodes that you would see is very similar, right? So like, for example, right from the main function, it would reach out to different other functions, and the pattern of it reaching out might differ. And sometimes it does affect in us trying to check if a particular application is a malware or not. The entire premise here is the kind of function calls that it makes, the number of times the calls were made. So these different parameters eventually led to us to decide whether a particular application was malware or not, right? So, okay. So in terms of graph kernels in machine learning, so this is, I think, one of the predominant aspects that we look at. So we ended up using something called as neighborhood hash graph kernels. So this is how the bit representation really works here. You will see node A, B, C. So these eventually get replaced with a 4-bit label, right? Now we started using this mechanisms for every function. So when I say a particular node here, it basically means a particular function. So as many functions an application would have, or as many API calls an application would make, based on that, these different nodes gets created, and then the number of calls to it basically eventually defines whether a particular application would be considered as a malware or a non-malware, right? Again, if you see every malware sample or every application for that matter, you eventually get a signature out of it. When I say signature, I'm not talking about in terms of the antivirus mechanism and the heuristic versus signature. I'm talking about the kind of calls it makes, the number of calls it makes. Of course, it's a mixture of the way heuristic works and the signature pattern works. But based on those calls it has been able to make, you eventually get to know if an application is malicious or not, the number of calls it makes. So what kind of function it is trying to use, or what are the different API calls it's purely making, right? So once we are able to generate the neighborhood hash graph, we are able to use hash graph kernels, the next aspect for us was to sort these hash values. So the functions that get created, eventually we were able to sort of create a particular graph based on whatever was the neighboring node. Let's say, for example, we have a node A, and whatever it neighbors to, so there would be a certain value that would be given, like a limited value, the number of total nodes that can get created, that can be used in this particular structure. And based on that entire neighborhood would be basically considered as one entity, right? Now, that entity will eventually get converted to a hash value. So for us to sort of keep a track on those values, right? So once that was done, so we basically then sort out the hash values, count the common labels that are present there, and then we go ahead and compute the coefficients. Now, the computing of the coefficients again will be part of the SVM mechanism itself, so which you will see further. So this is the FCG that we obtained from one of the applications that we had done for. So the application was hardly like 5 MB Android application. And the number of API calls, the number of functions that eventually got created. So every single line that you see, so the blue dots that you see are basically the nodes. The lines that you see here are basically the function calls that is being made, right? So this was just a very small application. I think it was like hardly 5 to 6 MB if I'm not even wrong. So these were the total number, and it becomes very, it's completely human unreadable. So this is the mechanism. So if you can see here, the analysis of the APK files, we basically listed down the app names first, and then the according SHA-256 and bunch of other details, the initial parameters that we are able to take, right? So now for every single application, what we basically again looked at was what levels of permission that these applications were asking, what were the sensitivity, and then probably other aspects, other metadata like summary and description, etc. Right? Now we'll look at, so this is the extraction of those API calls that were made from one node to other, right? So now we'll get into, so before we get into the SVM, I'll just give you a quick overview of what are the open source modules that we ended up using. So we use something called AndroGuard, NetworkX, Matplotlib. So these are all the Python-based open source libraries that we used for this experiment. And so the algorithm that we used was called support vector machines. I'm sure most of you are already aware of this. I think this is one of the widely used algorithm in the security industry, if I understand. So let's look at how SVM basically does it. So you see a two-dimensional space. So the plane that you see here would ideally be n minus 1. So when I say n is the dimension. Let's say if it is a two-dimension, the plane would be n minus 1, which is 1, right? So this is a single line you will see. If it is a 3D, you will basically a plane, I would say, right? Now, this is a two-dimensional. So the black dots that you see are the malicious applications, and the white dots you see are the non-malicious applications. So the plane that cuts across is the one that bifurcates between these two. The one that classifies, basically differentiates. Right? So now, so this is an example here in a two-dimensional space. You will see this is a feature space. Now, these are all the nodes, the different nodes that were generated by the functional call graphs. Now, they are again plotted over this feature space. Now, there could be other, like basically we would try to see a plane that can cut across this entire feature space that divides these two different functions, right? Now, the whole idea here is to draw a line that bifurcates, but also gives us a larger margin to expand, so that the lines or the dots that you see, the malicious versus non-malicious, that touches across these margins are the support vectors. So I'll talk what exactly what I mean. So let's say there could be another plane that could be drawn here, which could be able to bifurcate in such a manner. Now, you could also do it this way, right? There could be like multiple such kind of ways where you will be able to figure out if the differentiate between malicious versus non-malicious. Now, in such scenarios, there are high possibilities that something like one of the pattern or one of the nodes eventually would get misclassified. Now, there is a high possibility. So by default, SVM is of it's a hard classification nature. So there are other soft ways of classifying it, which eventually makes it which would end up basically giving out quite a lot of misclassifications. Now, there could be quite a lot of changes. There are quite a lot of parameteral changes that we can make, either in terms of the features that gets mapped, or the matrix that gets generated, or even post, even in like terms of changing certain parameters that we would initially take even before we generate the functional call graphs. So based on those is when we'll be able to sort of reduce down the misclassifications. Now, let's get into defining the margin, right? Now, if you take a plane like this, so there has to be a margin around that plane that would basically, at least the nodes that would touch this margin is basically called as a support vector. So I'll show you an example. So if you cut across a line like this, and the blue colored line that you see is basically your margin, right? And the nodes that are touching these margin are basically your support vectors. So based on this is basically the whole idea here is, as much as you're able to expand this margin, your classification is much better, right? So now, of course, there would be cases where the margins would be very small, and it becomes very difficult to say whether this application has a malicious content or not. Okay, so that was a mechanism that we used to now bifurcate whether these nodes, with the number of function calls it made, the number of functions that got generated eventually. Based on that, we were able to decide whether a particular application was malicious or not. Now, I know this is a little controversial when I say this out loud in a conference like this. The accuracy that we were able to see with these 900 applications for both malicious and non-malicious was around 78%. There was a 3% false positive rate. Of course, there were a bunch of other things like your true positives, true negatives, and all of those. But this is something that we were able to see in terms of accuracy. Of course, this is not like a hard rule that the accuracy would be this much, but it would eventually change based on different parameters that are used. So our process was pretty simple. We basically did a data analysis of the currently used algorithms out there on the internet, and in the community as well. So we did sort of revise over our approaches. Initially, we started off with doing k-means clustering, k-means mechanism, but that didn't really work out. And then we ended up going with SVM mechanisms. And this was the entire process that we followed. And then eventually, we were able to sort of come up with this experimentation. So what was the final conclusion that we were able to see is machine learning algos, of course, can be used for malware analysis, but it's a complementary feature that adds up to what the dynamic analysis already is doing, right? So it cannot be considered as one sole mechanism to differentiate if a particular application is malware or not. Of course, there could be a possibility that things could get misclassified. And getting feature space right is indeed a big deal, because what we are going to consider as a feature space, how are we going to even map them under one neighborhood clustering will matter the most. And these, again, models could be generalized in terms of getting, like for example, adwares, it was quite easy when we tried to do it in terms of finding out if it was a malicious or not. And, but we felt that with other set of applications, there was still some level of research needed. So certainly in terms of drawbacks, I would say when there were certain obfuscation techniques that were used on these applications, the SVM model was not able to differentiate whether if it was a malicious or a non-malicious application, because the functional call graphs that got generated, it was not able to sort of make a confirmed decision on those. So henceforth, it becomes a very tricky situation when there is an obfuscation that gets involved. So these were the references. There were a bunch of papers that we went through before we even went ahead and did this experimentation. So yeah, that's from my side, guys. Thank you so much.